We're going to start talking today about water. This is probably going to take maybe two videos. I'm not really sure. It's going to be more than one though. I'm going to try to keep them to about 15 minutes or so or less. In addition, there's some stuff in here where you want to review some of the stuff that we've talked about, including attraction for electrons on the periodic table, how that varies, chemical bonds, things of that nature. So let me just go ahead and work through here. Water is obviously very important. We've dealt with a little bit of it with the nomenclature piece. All right, so remember from Lewis dot structures, which is also something that perhaps you should review, and shape as well. Water has a bent shape. What's not shown here are the two unshared pairs of electrons on the oxygen. All right, so I don't remember if I've talked about this, so if I have, I'm doing it again, and if I haven't, here you go. So just to make sure you understand the difference between intermolecular forces and chemical bonds, and we talked about chemical bonds extensively a long time ago. So a chemical bond is between atoms within a molecule. Breaking and forming them is a chemical change. And remember we talked about ionic bonds, which are between charged particles, so between ions, so like sodium chloride has a sodium ion and a chloride ion. And they are held together because the positive sticks to the negative. Covalent is electron sharing. Okay, all of these, even the weakest, ionic bonds are the weakest, all of these are stronger than the strongest intermolecular force. Okay, a good analogy would be if you hold your hands up and you interlock your fingers. Separating your hands would be breaking intermolecular forces. Pulling your fingers off would be like breaking a chemical bond. Right? So intermolecular forces are between molecules. Breaking and forming them is a physical change. And as I said on the other slide, all are weaker than chemical bonds. There's three major types of intermolecular force. There's dipole-dipole, hydrogen bonds, and nonpolar forces, and these are all on the next several slides. All right, so for molecules to be polar, we've talked about polarity and bonds. Okay, polarity and bonds. Okay, there's two requirements for a molecule to be polar. It has to have polar bonds, and it has to be asymmetrical. So remember, for a bond to be polar, there has to be a difference in attraction for electrons. And so if you look at the periodic table, remember how attraction for electrons varies. As we move to the right, it becomes stronger. As we move up the periodic table, it becomes stronger. So the upper right-hand corner of the periodic table has stronger attraction for electrons. Right? In a polar bond, you have a difference. And so I remember I talked about covalent bonds being like a tug-of-war. So if you're pulling the electrons closer to you, if you're winning the tug-of-war, that means it's going to make you a little negative and it's going to leave the other side a little bit positive. Typically, polar bonds are metal-nonmetal. That is if you have ionic compounds, and then, of course, two different nonmetals. And then the molecule has to be asymmetrical. So you might want to review molecular shape, the PowerPoint for that. We did that before we went on lockdown, so it should be under lecture handouts. All right, so, and again, there's my beautiful drawings. So just as an example, this is a molecule that has polar bonds. So carbon dioxide is a linear molecule. It's got carbon, oxygen, carbon, oxygen. Remember this notation, the positive is on the positive side. So a carbon-oxygen bond is polar. The oxygen side is the negative side because oxygen has a stronger attraction for electrons. So if you imagine tying a rope to the carbon and pulling towards the oxygen, but then tying another rope to the carbon and pulling towards the other oxygen, would the carbon move? And because, no, it wouldn't, and that's because the polarities cancel. So the polarities cancel out. Though this has polar bonds, it is a non-polar molecule. Now, if we look at a molecule like fluorine monochloride, which is linear, again, fluorine is right above chlorine on the periodic table. That means fluorine has a stronger attraction for electrons. So in the FCl bond, the positive side will be the chlorine, the negative side will be the fluorine. And so what that means is that you kind of draw the electron cloud as being this line, the electrons being distributed between the fluorine and the chlorine. Remember we talked about electrons kind of being a cloud. Excuse me. The more negative atom is going to, the one with the stronger attraction for electrons is going to pull the electrons closer to itself. So that means that's going to give it a negative side. This notation, a lowercase Greek letter delta, means partial. So it's not a full charge because it's not ionic, but it's pulling the electrons closer to itself. So it's going to give it some negative character. If I pull electrons towards the fluorine, I'm pulling them away from the chlorine, which means it's going to expose the nucleus. This has a positive character to it. So kind of teardrop shape. This is a polar molecule because there's no cancellation. All right, the types of intermolecular forces are dipole-dipole, hydrogen bonding, and nonpolar forces. All right, so dipole-dipole, the word dipole means two poles, so that means there's a positive and a negative side. So a dipole is a polar molecule. And the bottom line is something we talked about very early, positive sticks to negative. So if you look below here, here's your fluorine monochloride. The fluorine is the negative side of the molecule, the chlorine is the positive side. Another molecule, this one here, the negative side of this molecule is going to stick to the positive side of this. And just so you can kind of get a good feel for it, this sticking between the positive of one molecule and the negative of another, the sticking is the intermolecular force. The bond between the fluorine and the chlorine is a covalent bond. In this case, it's a polar covalent. It's very important to know the difference between a chemical bond between molecules or between atoms within the molecule and an intermolecular force between the molecules. This is more of a sticking, where this is a full-on chemical bond. All right, hydrogen bonding is a special case of a dipole. It has its own name because it's extremely common in nature. And very specifically, hydrogen covalently bound to oxygen or nitrogen. Frankly, you can include fluorine and chlorine, but we just don't see it that often, sticking to an unshared pair on another molecule. Remember, an unshared pair is a negatively charged spot, right? Now, remember, oxygen and nitrogen have the strongest attraction for electrons on the periodic table other than, say, fluorine and chlorine, and that means it's going to pull electrons away from the positive, away from the hydrogen, making the hydrogen positive. So then you're going to get a negative positive. Okay, hydrogen bonds are the strongest of intermolecular forces. Dipole-dipole kind of is in between. So water is a great example. So if you look at water, here's an OH bond, and this is a covalent bond. This is a covalent bond, covalent bond, covalent bond. This bond has a positive on the hydrogen and a negative on the oxygen. On this molecule, there's a negative on the oxygen, also the unshared pair. And so this hydrogen sticking to that unshared pair, that is what's called a hydrogen bond. It's a misnomer because it's called a bond. It's technically not a bond by definition, but we just call it that because we call it that, right? Just to get the distinction. Has to be oxygen or nitrogen. Right? Nonpolar forces are the weakest of intermolecular forces. They're between nonpolar molecules. How they work, we're not going to really get into that, but just kind of consider electrons flop around a little bit. They don't just stay in one place, all right? But remember, and so that means that they can move from side to side. You can get temporary polarities, but they're very weak. Just remember, nonpolar molecules share the same nonmetal, or if they have almost the same attraction for electrons like carbon, hydrogen. Right? So if you have nonpolar molecules, they're going to have nonpolar forces, and these are the weakest. All right. So let's spend just a couple minutes about talking about water. Water has some really interesting properties, mostly due to its polarity, its shape, and its ability to hydrogen bond. I also want to point out, I'm drawing the molecule this way. So if the two hydrogens, if you remember oxygen, if there's 1, 2, 3, 4 sites, right? 2 unshared pairs and 2 bonds, that means there's 4 sites. 4 sites means it's approximately tetrahedral. That means if these 2 hydrogens are in the plane of the screen, these 2 unshared pairs are actually coming out at you and going behind you. You might want to review your slides on molecular geometry. But it's kind of important to realize that because that means a hydrogen bond is actually going to come out of the screen and behind the screen that's sticking to this. Right? So you can see in ice, water forms this really open structure. Right? So we're going to do this slide, and then we'll probably stop and pick up here. So let's talk about the relationship of shape to the properties. So like I just said, the clouds are tetrahedral, so the bonds are in the plane, the unshared pairs are in front and behind. Creates a very open structure. So if we back up a slide, see this open structure here? So when water freezes, remember, where does water freeze? It can freeze in the air, forming snow and hail, right? It can freeze on the ground. It can trap molecules of oxygen, gas molecules, and we talked about that in terms of ice cores. Remember that before? Also, another interesting thing, because it has such an open structure, water is unusual because ice floats. That means the density of ice, the solid, is actually less dense than the liquid. Now, if you think about some biological implications, if you think about how do plants first start? So you have some rocks, right, caused from volcanic behavior. When rocks come up, when they're lava or magma, when they cool, they're not homogeneous, and so they cool at different rates. And then, of course, heating and cooling, they'll get cracks. If the rock gets a crack in it and some water gets in there and then it freezes, it's going to expand, and it actually makes the rock get a little bit, makes the crack bigger and bigger and bigger over time. And then seeds can get in there, and that's where you first start getting plants in rocks and so on and so forth. So there's all sorts of interesting implications. You could argue that life on this planet would not exist as we know it if it wasn't for the structure of water. Okay, I'm going to stop right here, and then we'll pick up here on the next set of slides just because it's a good stopping point.